Alright guys, here are the application problems on page 85. And the first part of this is it says to look up at the table of specific heats on page 82. So make sure you look at page 82. There's a chart on the lower right hand corner of page 82. And we're going to use those values. And that chart starts with aluminum and ammonia and carbon dioxide. So take a look at those. We're going to use those values in these calculations. So the first question is how much heat? Question 1. How much heat is absorbed by 1 gram of iron when it is heated by 15 degrees Celsius? So what I like to do is I always like to write down what was given to me. So I'm going to write down the mass. The mass equals 1 gram, and the temperature change, or delta T, is 15 degrees Celsius. So then we have to figure out which equation do we use. Well, they gave us an equation of Q equals C M delta T. And C is what comes from the chart on page 82. Mass comes from right here, and delta T is right here. So we just have to figure out what the C is. Now the C is dependent upon the type of material. So if you go to page 82, and you look up, this is iron that they asked us to look up for, and iron has a specific heat factor of 0.45. So C equals 0.45. So the only thing we need to do is put all these things in the equation. So this is going to equal 0.45 times the mass, which is 1 gram, times delta T. And that then, if you multiply all that out, you would actually end up with 6.75 joules, or it's about 6.8 joules. So the things to learn from this part of this problem is we wrote down what was given right here. We also have to figure out what equation to use, and that's sometimes the most difficult thing to use. And then we have to look up some information in the chart based on the fact that this was iron. So let's look at the next problem, problem 2. And if you need to, take some time and pause the video to read the problem and make sure you understand it. So this time, we're going to take equal masses of copper and aluminum, and we're going to heat them from 22 degrees to 100 degrees. Which object absorbs more thermal energy during this temperature increase? So what we want you to think about is, which one takes more energy to increase in temperature? So you want to spend some time thinking about it, and first thing we want to do is let's write down the materials that we have: copper and aluminum. And if we look up at that chart, our C factor for copper, if we look at the chart on page 82, it is 0.38. And for aluminum, it is 0.90. So what that means is that aluminum, its specific heat, this C factor right here, it's greater than copper's specific heat right here. And so more energy is needed to raise the temperature of aluminum. So every time you want to raise it 1 degree, you have to use, if you have 1 gram, if you want to raise it 1 degree, you would have to use 0.90 joules. But if you had 1 gram of copper and you want to raise it 1 degree and it's 1 gram, you have to just use 0.38 joules. So this actually takes more energy in order to raise it a degree, because the unit of this, the C, equals 0.90 joules per gram degrees Celsius. And it's not writing right now, so there it is, Celsius. So it's just important to remember that. So the answer to that one would be aluminum, and that's just based on looking up at the chart. Let's do another calculation. Number 3. This one says 5 gram sample of gold requires 12.9 joules of energy to heat it from 15 degrees to 35 degrees. Calculate the heat capacity of the sample and the specific heat of gold. So let's write down what we've been given. So we've got a mass. It equals 5 grams. That's kind of easy. We have the total energy. Energy that was used was 12.9 joules. Okay? And we have delta T, which is the change in temperature, which equals 35 minus 15. Remember, it's always the last minus the first, so that equals 20 degrees. So the heat capacity, it's given by the same equation, but it's modified a little bit. The equation is C equals Q, which is the amount of energy, so Q equals energy, divided by delta T. So we're going to have 12.9 joules divided by 20 degrees Celsius. And that equals 0.645 joules per degree Celsius. Or that's about 0.65 joules per degree Celsius. So that would be your answer for the first part. Now they want to know, well, what is the specific heat? Because this just calculates out what the heat capacity was for that specific sample. If we want to know the specific heat for gold, we have to use the mass. The only thing we have to do is take, for the specific heat, it's a little c equals the big C divided by the mass. In this case, it's 0.65 joules per degree Celsius divided by the mass, which is 5 grams. And we would get 0.13 joules per gram times degrees Celsius. Now let's take a look real quick to see how close this comes up in the chart. Oh, we don't actually have it in the chart. We don't have gold in the chart. So I guess you can't look it up. So let's take a look at the next question, number 4. And again, I want you guys to take your time with these to try and understand them. Number 4, the question is, a sample is added to a calorimeter with 75 grams of water at 23 degrees Celsius. Now remember, a calorimeter is something that measures energy, and what they do is they put the sample into it, and then they wait until everything's at thermal equilibrium. In other words, all the objects are the same temperature. When they find out that everything's at the same temperature, then they measure the temperature and they can see how much heat is gained. So a sample is added to a calorimeter with 75 grams of water at 23 degrees Celsius. At thermal equilibrium, the temperature is 25 degrees Celsius. How much heat was gained by the water? So this is a little bit more difficult because we have to rearrange some things, but let's just throw some information down that we know. So the first thing that comes up in the write-up, in the question is, we know the mass, it's 75 grams of water. We know it's water, that's important. And then we know that the temperature change of that water was 25 degrees minus 23 degrees. So that equals 2 degrees. Okay? And they want to know how much heat was gained by the water. Well, heat is joules, or energy. So our equation is going to be Q equals little c times the mass times delta T. And we just need to know, well, what is this C right here? Well, this C for water, we look up at our chart. For water, it's 4.18. C equals 4.18. So actually, we have 4.18 times the mass of 75 grams, and change in temperature is 2, and we actually have 627 joules. So fairly easy calculation. But again, it gets confusing when you start to look at all these different numbers that are thrown into the problem. You have to think it through. So most of these equations are just using this simple, or most of these problems are just using this simple equation, and they're rearranging it using algebra. So let's look at number 5. This one we may not have to do any calculations, but let's just talk about it. 5. We have two 50-gram metal blocks, one made of lead and the other of iron. So I'm going to write this down while we're speaking. Mass equals 50 grams, and we actually have two of them. One is lead, and one is iron. And what we're going to do is they're going to heat both of these to a temperature of 100 degrees. So you've heated both of these up, and then you're going to take both of them and put them in two separate identical calorimeters that each have 100 grams of water in it. And the starting temperature is 20 degrees Celsius. Which calorimeter will have the higher temperature at thermal equilibrium? In other words, this heat that is in each of these objects, let's call this either the lead and the iron, this heat that's in there is going to spread out to the water. And the question is, which of those waters in the calorimeter will actually be hotter? Well, the answer really comes down to the chart. Let's take a look at the specific heat of iron and lead. Well, on the chart, we see the specific heat of iron is 0.45. Oops, 0.45. And for lead, it's 0.13. So that means iron takes a lot more energy to increase its temperature. So in order to get it to 100 degrees, you have to give a lot of energy to iron. Once it has all that energy, then it's going to dissipate that energy in the water. And because it has all that energy, then the temperature in the water is actually going to increase more. So iron would be the answer to this. And it's simply because the specific heat of iron is much greater than for lead. When you heat up lead, you don't need as much energy to increase it to 100 degrees. Okay, that's all we have for you, and let me know if you have any questions. Thanks.